recording the class. I've started recording, so please don't unmute yourself. Please. Please mute yourself.
সঙ্গীত তো খায় বউ কি হলো
Sound is not hearing.
কথা বলছিলাম দোকানে কথা বলছি
आवाज नहीं आ
Can you hear me now?
Yes, ma'am.
Okay, somehow someone had
Yes, ma'am.
muted me.
Yes, ma'am.
Okay, but someone from the audience had muted me because I just came back to the screen and I found that I was muted. Listen, this is a class. We are all in a very difficult situation. We cannot go to college. We are having to take class at such odd hours from our home, 7 at night. All right, at the end of a day. I had gone to college today. I was working throughout the day in college, uploading marks and doing exam related work. So I'm extremely tired right now. So please do not create any disturbance. Please join the class only if you are interested in studying and listening to what the teacher is saying, the subject, understanding the subject. If you are here to do some, naughtiness, then you are welcome to leave the class. Please don't join the class to create disturbance. Someone had muted my mic and someone was constantly unmuting his mic. So please don't do all this. All right. I hope everybody can hear me now and everybody can see my screen.
Yes, ma'am.
Yes, ma'am.
Okay. So this is okay. So this is what we are doing. This is the code. Physics general CC1 is your theory. This is the code, and that contains the mechanics portion, out of which we are going to do vector algebra and vector calculus. This is my name, Dr. Kamulika Hajra from the Department of Physics, AJC Bose College. Okay. All right. Okay. So the first thing that I'm going to do is I'm going to ask you a question, because as I told you, you all have done vector, you have learnt about vectors in high school and in your +2. So the first question the first thing that we're going to do in this class is ask a question, and that is, how do we define a vector? Can someone unmute and tell me how we define a vector? Anyone? All of you have learned about vectors.
Ma'am, it is a quantity which has magnitude and direction.
Okay, so very good. I don't know who was this. I don't know your names, and it makes me very, very uncomfortable when I don't know the names of my students.
Ma'am, my name is Anish.
Okay, Anish, thank you for the answer. Absolutely correct. We have physical quantities. We see physical quantities all around us. And at one point of time in high school, say in class 9 most probably, we were told that, look, you can see things all around, but although till now you were just weighing things and measuring distances and doing sums on speed, etc. But just remember that these things that you see all around can be categorized into two groups. A particular group which have only magnitude, for which you can only consider the magnitude, is called a scalar. For example, mass, for example, volume, these things. Whereas there are certain other things for which not only the magnitude but also the direction in which the quantity is pointing is important. So that is called a vector. So answer to the definition of a vector is a physical quantity that has both magnitude and direction is called a vector. Okay, so you can, I'm sure all of you can remember your class 9 and 10 definitions and physics books where it was written how displacement is a vector but distance is a scalar, how speed is a scalar whereas velocity is a vector. Okay, so whenever you associate a direction, a sense of direction with a quantity, or if there is a quantity which does not make sense without a direction. For example, if you say, I'm applying a force on a body and the body is moving, then it doesn't make sense if you just say the force, I'm applying a force of say 5 newtons. The next question that immediately will be asked is, in which direction are you applying the force? So such quantities which doesn't make sense unless you say the direction in which they are acting are called vectors. Okay. So my next question, and you might think that this question is a bit out of context for this class, but even then I'll ask this question. And this question is about electric current. Okay. Is electric current a vector or a scalar? Can someone say, is electric current, electricity I, charge by time?
Vector.
Okay. Someone say vector. Does everybody agree with her, vector?
Yes, ma'am, vector.
All of you agree that current electricity is a vector?
Current is a scalar quantity.
Okay, some say vector, some say scalar.
It's a scalar.
Let's see how we define current electricity, okay? Since there is a debate, I mean, all of you are not in consensus about the nature of current electricity. Let's see how we define. So this is how we define current, okay? Limit delta t tends to 0, delta q by delta t. So it is equal to dq dt. So it is a time derivative of the charge, time rate of change of charge. So obviously charge is a scalar, time is a scalar, and you can see that we cannot see any vector quantity in the definition of current, right? So mathematically, if you look at the definition of current, you can see that it is a scalar quantity. But of course, you know that in Yes, someone is trying to say something. Your voice is cracking. Your voice is breaking. Okay.
Both are
So
actually current, electric current is a danger quantity.
electric quantity is a scalar quantity. Yes. Yes, it is. Yes. Yes.
Danger quantity, quantity.
যেই বলছো না তোমার ভয়েসটা একদম ক্র্যাক করে যাচ্ছে, আমি শুনতেই পাচ্ছি না, একদম ব্রেক করে যাচ্ছে। তুমি লিখে দেবে, লিখতে পারো। You can write if you want in the chat box. Okay. Okay, I'll continue. Okay, so we had asked this question. Okay, now we know that in a particular wire, now current flows, of course, when there is a potential difference between 2 points, and we know that electrons, right? Electrons move from a region where there is a higher concentration of electrons to a region where there is a lower concentration of electrons, and conventionally we take the direction of flow of current opposite to this, right? We take the direction of flow of current opposite to the direction of flow of electrons. So the region where there is a dearth of electrons, where there is lesser number of electrons, that is called a positive potential, a higher potential. And the region where there is more electrons, that is called a lower potential or negative potential, and current flows from a higher to a lower potential. So definitely when there is a flow of current, a direction is definitely involved because electrons move in a particular direction and the opposite direction is taken to be the direction of flow of current. Yet we cannot call current a vector. Okay, so why is this confusion arising? This confusion arises because until now the definition that we have known of vectors, a physical quantity that has both magnitude and direction, that needs to be modified. Just having a magnitude and direction does not suffice a physical quantity to be called a vector. If that would have been the case, then we would have to call current, electricity a vector too, but we cannot do it. So the new definition of vectors is a physical quantity that of course has both magnitude and direction, and additionally obeys the laws of vector addition. Okay, so now if you are asked to define a vector, you will not just say that it has magnitude as well as direction. Okay, along with that, that's correct, that's not wrong. Of course, a physical quantity which has magnitude and direction can be called a vector. But if you say only that, then at least one quantity in the physical world, that is current, will give you a confusing question. So to avoid that, you will say that physical quantities that have both magnitude and direction obey the laws of vector addition are called vectors. Okay, is that clear to everybody? So this is the new definition of vectors. You will soon see that till now we had called, we had said that distance is a scalar, whereas displacement is a vector. Area is a scalar, volume is a scalar. But we will soon see, if not in this class, then definitely in our next class, that we can actually associate a direction with area. And when we call an area a vector quantity, that vector quantity can be made to obey the laws of vector addition. So it can be called a vector quantity. Okay. But I don't want to confuse you by saying this without proper backup. So we'll discuss this in our when and where the time comes. For the time being, let's continue with our preliminary discussion of vectors. All right. Just whatever you knew were all correct. I just added some information saying that along with the fact that it has to contain both magnitude and direction, it also has to obey the laws of vector addition. Current does not obey the laws of vector addition. Addition of current follow a totally different set of laws. Therefore, we cannot say it is a vector quantity. To be called a vector quantity, the quantity has to obey the laws of vector addition. Okay. Now, any vector may be represented in two ways. All right. I'm not talking about the print. You know that in print, if you want to represent a vector in writing, when we write, we usually write a letter and, draw an arrowhead on the letter, which means it is a vector. And in books, sometimes it is given in bold print so that you can understand that it is a vector quantity. I'm not talking about that. I'm saying that any vector can be represented in two manners. And what are those? First is the geometrical representation. You know all this. You've done this, but probably no one has told you before in such precise way how the two representations are separate. That is what I'm doing in this class. Okay. So geometrical representation, simple. Okay, this is, you all know this. You start at a point and you end at a point. The tail and head of the arrow are in this manner. The length of the arrow gives you the magnitude of the vector, and the direction of the arrowhead gives you the direction of the vector. So simple as that. Okay, so this is the geometrical representation. Correct. So suppose you have a vector A like this. So the length of this line segment is the magnitude of the vector A, and the direction of the arrowhead on this line segment gives you the direction of the vector A. And we have another vector B. Once again, the length of the line segment is the magnitude of the vector B, and the arrowhead gives you the direction of the vector B. Now, suppose you are asked to add the vectors A and B. How will you add the vectors A and B? Very, very convenient. Why? Because if you parallelly displace a vector, nothing happens to it. If you take a vector, say you take vector A and displace it parallelly to a new position, then nothing happens to it. Its magnitude and direction remains the same. It remains the same vector. So you parallelly displace vector A to a convenient place and parallelly displace B to a convenient place, such that the end of B begins from the, the tail of B is the same as the head of A. Then the law of vector addition, which is known as the triangle law of vector addition, says that A plus B is equal to vector C, which is the other arm of the triangle. Okay, I have not written this down, the law, because it's written in all books, and you've probably done it in your +2s also, that if the two sides of a triangle moving in a particular direction forms the two vectors.